Today we're looking at the finite square well of quantum mechanics in Python. This is going to be the first video in a sequence of videos where eventually I want to build up to finding the energies of an electron in a crystal lattice. Now, a crystal lattice of protons is essentially just a sequence of wells, right? So if we can solve the Schrödinger equation for one well, we can use approximation methods to get the energy eigenvalues for a sequence of wells, and we'll do that in later videos. Anyways, let's get right to it. So there's nothing too fancy with the packages here, other than the fact, I guess, that I'm using a dark background now. I think the contrast should make it a little easier to pay attention to things in the video. Plus it looks a little bit more aesthetic, so let me know what you think. The only complicated package we're using here is the tridiagonal matrix solver. What we're going to do is we're going to solve the Schrödinger equation, and it's set up as where the Hamiltonian is a tridiagonal matrix. That's a very large matrix as well. And this is a very efficient way for solving large matrices, getting the eigenvalues, which are the energies, and the eigenvectors, which are the wave functions. So we'll start by reviewing the finite square well. It looks like this. There's a potential energy and position, and it's a well because there's less potential here than there is here. So there's going to be bound energies where a particle is sort of inside the well, where the energy is less than zero. And then there's going to be energies greater than zero, where of course it can escape the well. And so that's sort of what the well looks like here. And we set up our Hamiltonian like this. H is minus h bar squared over 2m, d squared dx squared plus v of x. This is just the classic Hamiltonian for position wave functions. And we use it to write the Schrödinger equation, h sigma z sigma, like this. I just plug h here and I get this equation. This is just classic. You've seen this before. But what I do is I want to make this dimensionless. I do this in all my videos. I want to solve this using dimensionless quantities. So I'm not dealing with h bar and m and v naught and a and all that stuff. So I multiply each side of the equation by 2ma squared over h bar squared, and this cancels out, and then the a gets factored in here. X prime is equal to x over a, so this is a dimensionless distance, by the way. I have this quantity here and this quantity here. And the reason I define x prime, which is x over a, is because now the well goes from -1 to 1, as opposed to negative a to a. So it's a little easier to keep track of quantities that way. We're setting it up dimensionlessly. So then what I do is I define v prime is 2ma squared over h bar squared times v, just to bring all this together into one dimensionless quantity called v prime. And I do the same thing with the energy here. E prime is 2ma squared over h bar squared. What this does is it makes the problem a little bit simpler, right? I now have this quantity here, which is my new Schrödinger equation, where v prime is dimensionless and e prime is dimensionless. And the reason is because this quantity here, 2ma squared over h bar squared, has units of inverse energy. So I have inverse energy times energy, so v prime is dimensionless. And now this is the new equation we have to solve, which is much easier to solve on a computer. I just have a second derivative, I just have a number here, there's no dimensions to it, and I have a number here. So this, of course, is a lot simpler to look at and also solve. Now, inside the well, we have to deal with the potential. And you might want to say, well, what is v prime equal to, right? I need to feed in what v prime is equal to in this equation in order to solve it. And so what I do is I need to relate this to v naught inside the well. I mean, outside it's just 0, but inside it's related to v naught. And so if you note that v prime is just v divided by h bar squared over 2ma squared, what it tells you is that v prime naught, which is inside the well, right, is a dimensionless number. It's just a number, like 2, 3, 4, and it tells you how many h bar squared over 2ma squared there are in v naught. And this sort of relates the different energy scales of the problem, right? This is one energy scale that tells you about the mass and the width of the well. So that's the scale of sort of the particle's mass and width of well. And v naught prime is another energy scale, which is the depth of the well. So that's sort of related. This is like a relation quantity of the problem. And so, for example, if v naught prime is equal to 6, it tells you that there are 6 times this energy scale, and that's the depth of the well. In summary, when you solve the problem, the first thing you need to do is decide what v prime is inside the well. And that's just how many times h bar squared over 2ma squareds there are per v naught. So it relates the depth of the well to sort of the width of the well and the mass of the particle. And that could be like 6, 8, 10. It depends sort of what you care about for the particular problem. Then you would solve the eigenvalue equation above, this equation here, using some sort of method. We'll do it analytically first, and then eventually we'll do it numerically. And then you get your energies E prime. Of course, these are dimensionless numbers. And if you want the true energies of the problem, like this is like 4, 6, 8, the energies are given by h bar squared over 2ma squared times E prime. So that allows you to get the specific energy levels of the problem. And of course, this works for any well, any massive particle, but it is for a specific V naught prime, right? So that's the only thing that you need to decide. And then it's arbitrary. You can plug in any mass you want, any well width you want, and it will work. Similarly, the obtained eigenfunctions, psi of x prime, where x prime equals x over a, which is dimensionless, you can get the real eigenfunctions as a function of position just by multiplying inside by a. So psi of ax prime, which is equal to psi of x. And that's just using this relation here. So that's how you get the eigenfunctions. For now, what I'll do is I'll drop all the primes just because, it's a little bit complicated writing this out with primes every time. But just remember that I'm dealing with dimensionless quantities, and I still need to follow these steps once I've finished solving the problem. So what we're going to do is we're only going to look at states of the particle that correspond to bound energies. So this is where the energy is less than 0, or it's like trapped in the well. And so when energy is less than 0, by the way, the square root of negative E, well, negative E is positive, so this is real. And we'll use this to define some quantities. So we'll write our equation like this. Inside the well, we have an equation that looks like this, and we rewrite it so that we have d squared psi dx squared, remember x is dimensionless here, is equal to minus k squared psi. This is like a common, easy to solve differential equation, where k is equal to the square root of e plus v naught, right? That's just by definition. And we conveniently define k in this way so that we can write our equation like this because we know the solution to this differential equation. Outside the well, of course, the potential is 0. So we just have an equation that looks like this. This is a very easy to solve equation. And then we'll define L in such a way that L is equal to minus the square root of minus E. And this is also an easy differential equation to solve. We have K and L, which are real numbers, by the way. You can check that these are just real numbers. And when you have a differential equation minus k squared, or real number squared times psi, or real number squared times psi here, there are simple solutions to that. And they're sort of given like this. There are, by the way, even and odd solutions. So inside the well, where minus k squared psi, that's either a cosine or a sine solution. These are the even and odd solutions to this equation. Whereas outside the well, where I have L squared times psi, this is just an exponential function that solves this differential equation. And so that's why I have a e to the lx and a e to the negative lx. You'll note that e to the negative lx and e to the positive lx are both solutions to this problem. But when I'm determining sort of the solution of the wave function, we can't have the wave function blow up outside of the well. And so in the negative x region, so x is negative here, it has to sort of exponentially decay, which is what this does. And then same thing with positive x. So I only choose these solutions outside of the well. Same here, and I have cos and sine. So we can combine these with the boundary conditions, that psi and d psi dx are continuous at the boundaries of -1 and 1. And so I sort of relate quantities here. So I plug in x equals to 1, and I get two relations, one for the function and one for the derivative. And if I divide these together, I get k tangent of k is equal to L. And this only depends on the energy and the potential energy. So I get an equation that looks like this, right? And I can solve this equation and I get the energies that correspond to bound states of the well. And this is something that we have to do numerically. Same thing with the odd functions, and I get this other equation here. So there are two equations that I need to solve. This equals the square root of negative e, and this equals the square root of negative e. So I have these two solutions here. As a function of energy, I know what V naught is. I determined that at the beginning of the problem. And I plot this as a function of energy on the left-hand side, and I plot this. And the points where they intersect, that solves this solution, right? I want the e's such that these are equal. And same thing here. So what I do is I basically plot the square root of negative e, look for the intersection points, find the corresponding energies, and those are the bound energies of the well for that particular value of V naught. So let's compute some energies. So I'll have a value of V naught equal to 36. And then I'm going to look at, 100,000 values of E between minus V naught and 0. That's just for plotting these two functions here. And I get the right-hand side and the left-hand side of the two equations. So the right-hand side is just the square root of negative E, which I have here. Then I'll look at the left-hand side of equation 1, the left-hand side of equation 2. and I have them sort of looking like this, and I can plot them next to each other like this. And so the red here is the square root of negative e that I have here, going from negative 36 to 0. And then these blue lines are both the left-hand side of equation 1 and equation 2. If I just look at them separately, right, this is sort of the equation 1, and this here is equation 2. So these intersection points, I go down and I find the energy, and those are the corresponding bound energies of the system. So just by looking at this plot above, there are 4 intersection points. What that tells you is that there's 4 bound energies for this finite square well. And if I want to find these energies numerically, rather like if you want to find intersection points between 2 curves, like f of x and g of x, what you do is you take f of x minus g of x and you look for the zeros. That's typically how things are done numerically. So here I have f1. f1 is just right-hand side minus left-hand side 1. And I look for points where that's equal to 0, right? That's just how you do it numerically. Same thing with f2. It's just right-hand side minus the left-hand side 2. And you notice that I have this little epsilon here. This is a little numerical trick. And I add it here. It's a very small number. But what it does is it stops the tangent, because I have a cotangent here, which is 1 over tangent. And this blows up when e is equal to negative v naught, right? Cotangent of 0 is infinity, and I don't want that. And so what I do is I add a little small number here, and this sort of stops that from occurring. And so I can get my f1 and f2, and now I plot these functions, right? And now I just have blue curves. And what I do is I look for the intersection points with 0, right? All I'm doing with these 2 equations here is I'm doing this minus this equals 0, and then I solve for energy. So I just have 1 curve, 2 curve, and I look for the intersection points here. And those correspond to the bound energies. So I have my energy array. It's just a bunch of different energies. It goes from negative 36 to 0, which is minus v naught to 0. And I want to find the points where this intersects with 0. And this is where it gets a little bit tricky, and we'll break it down. The question is, how do you actually find the zeros of those curves? Well, the first thing I'm going to do is I'm going to take the sine of f1, right? f1 is just these blue curves here. So if it's negative, the sign is negative 1. If it's positive, the sign is plus 1. So if I look at the sign of this, it's like negative 1, negative 1, negative 1, negative 1, and then plus 1, plus 1, plus 1, plus 1. And if I take the difference, the consecutive difference, so this minus this minus this, and do that for, all the different pairs of the array, which I just call the np.diff function, I get 0, 0, 0, 0, 0, 0, right? Because the difference between all these is 0. But as soon as it switches sign from negative 1 to plus 1, I have minus 1 minus plus 1, right? And so I'll get 2. I'll get a value that isn't equal to 0. And same thing here. So by looking at the location in this array where the values are not equal to 0, it tells me about the energies corresponding to these intersection points with the x-axis. So if I want the points where this isn't equal to 0, I can call the np.where function. This gives me the indices of the array corresponding to non-zero energies. So it says at the index 5,000, 6,000, whatever. These are just like index values of the array. So these are the indices, and it turns out these are the indices right before it switches sign. So it's like the point right before this, the point right before this, etc. And so what I want to do is I'll define these as my zero crossing indices, like this. And so if I want to get like the average energy right before it changes sign and right after it changes sign, right? What I'll do is I'll take my energy of my zero crossings and I'll add 1 to those indices like this. So this is like all the points right before it switches signs, and then the energy right after it switches signs, and I'll just take the average between those. So I get sort of an average value there. So I'm not biased at all. And then this tells me my energies. Now it turns out there's a mistake here, right? And this is something you got to be careful with the tangent function, because although it's switching signs here, right, it's also switching signs when it goes off to positive infinity and then switches to negative infinity here, or it's not actually infinity, but it's really large value and then really negative small value for the numerical stuff we're dealing with here. And so we need to make a way so that it doesn't take into account the energy switching from here to here, right? Because I'm getting 4 energies. It turns out there's only 2, right, for the first curve. If I just look at the first curve, I should only be getting 1, 2, right? And then there's no other zero crossings here. And so in order to prevent like this switching sign point and this switching sign point, there's a little trick that I do. So what I do is I look at the values, right? I have my F1s, which is just this blue curve here. I can look at that. It's just an array. And when it gets really, really large, I don't want to take into account those points where it switches signs. So what I do is I take the absolute value of these F1s, which tells me how large the curve is at that point. And I want to look only at values, and this is just arbitrary for this problem, but I'll say, well, where they're less than 3. Because I know they're going to be less than 3 here, and I know they're going to be less than 3 here for consecutive points. So let's look at values where this is less than 3. So this currently gives me an array of Booleans. What I'm going to do is I'm going to change it to type float, as type float, like this. This will turn it into 1s and 0s, like this. So what I do here is I plot this function as a function of e, and this is where it's less than 3. So what it means is that I'm only looking for these intersection points where this is equal to 1. So I'm only going to look for intersection points here, here, and so there's basically 2 regions, right? And so what it means is that this region where it's equal to 0, right? Just looking here, it's equal to 0. I'm not going to consider sign flips in that region. That's essentially what I'm doing here. So that allows me to ignore the sign flipping as it goes from positive infinity to negative infinity here. So the question is, how do I actually implement that? Well, I have my difference array here, like this. Now let's look at these 2 arrays. These are my differences, 0, 0, 0, and then there'll be places where it's equal to not 0. And then I have this array here, 0s and 1s. And what I'll do is I'll multiply these 2 arrays together, and that what it'll do is the zeros of this array, if it's equal to a sign flip, but it's not less than equal to 3, which are basically these locations here, it'll turn that non-zero value into a 0, right? Think carefully about what I'm doing here. I have this array tells me where the sign flips are, and this array tells me only look for sign flips in certain regions. And I multiply them together, and where values of this are not equal to 0, they'll be canceled out by this array here. So it says, well, this is not less than 3, or this is not less than 3, the absolute value, so we're not going to consider a sign flip in that region. Now, it's a little tricky because the length of these arrays aren't quite equal. If I look at the length of this array, it's 100,000. But the length of the difference array, since I'm taking consecutive differences, is 1 less, right? Because I'm looking at pairs of values. It's going to be 1 less. So what I'll do is I'll index this array as follows. I'll only take up to the negative first value, like that. And now I look at the length of this array, and it will match the difference array, like that, right? And so what I'll do then is I'll multiply these 2 arrays together. And I get something that looks like this. And now I'll take np.where. It will give me the indices where this isn't equal to 0. And now I only get 2 indices, right? The 5023 index and the 44129 index. And so then, of course, I only care about this, right? It returns a tuple, but I'm only going to take the first element, which is the array, that array here. And I'll define this as my 0 crossings, indices, of course. And then if I want the energies, of course, I do the trick where I take the energy at the 0 crossings, and I'll delete this here, and I'll post this back up here. So I have my 0 crossings, like this. These are indices. Then I take my energy at the 0 crossings, which is the point right before the crossing. The energy is just after the crossing here. So I get an energy here, an energy here, and I take the average between them, and that gives me my energies. And I get minus 34 and minus 20, right? Those are my bound energies of this particular well, where the well has a depth of minus 36. So all this cell is doing is I get my F1s, which are the first blue curve, and then I also get my F2s, like this, the other blue curve. I get my even, right? 0 crossings, that's like this equation here, and my odd 0 crossings here, and I'll get 4 different values, right? Like I said. And so I get my 0 crossings even points, 0 crossings for the odd solutions. Then I take my 0 crossings, I sort them, right? Because there'll be indices, 2 indices, kind of like separate arrays. I concatenate those arrays together, and then I sort them from smallest to largest. And then I get my energies, and I call this method 1 because we're also going to solve it numerically as well. And I look at my energies, and I get the following points here. And I confirm this with a textbook, and these are indeed the correct energies that we expect. What this tells you, for example, is that the first excited state of this well, E1 prime, right, this is the ground state here. This is the first excited state, is minus 28.82. That's E1 prime. That's the dimensionless number. And if I follow step 2 of this instructions up here, the energies are equal to h bar squared over 2ma squared times E prime. So what it tells you is that the first excited state of the well is equal to minus 28.82 times h bar squared over 2ma squared. So hopefully that made sense. Now we're on to method 2. We're going to solve the whole thing numerically. And we'll start with this equation here. And there's no primes shown in this equation. This is an example of an eigenvalue problem over a continuous domain, x. We have a function. I want a function where you take the derivative and you add this potential and you operate on this function and you just get the function back times a constant. That's what an eigenvalue problem is, right? This is with derivatives and functions though, but we can turn this into a matrix equation if we make discrete points in x. So I'm going to discretize in x, so there's n discrete points in x as opposed to a continuous x domain. That means it can only take on values xi, x1, x2, x3, x4, x5, and the spacing between them is delta x. That's the convention. And then a function, or like psi here, or v, these are both functions. Well, fi is defined as the function at that discrete point xi. And so I have xi and psi values. Also, I have vi values, because this is a function too. I use the fact that the second derivative of a function at a discrete point, xi, could be approximated like this. This is the discrete approximation to the second derivative. And then I can rewrite the Schrodinger equation, this equation up here, just like this. And this equation applies to every single point psi I. But this, it turns out, is a matrix equation, right? I have psi I minus 1, psi I plus 1. If we think of psi as a vector of like psi 0, psi 1, psi 2, psi 3, psi 4, this is just a system of linear equations in psi. And if the wave function decays like sufficiently fast outside the well, we can assume that the first point and the last point are both equal to 0, and those are our boundary conditions. So this equation up here, written for every single psi I point from psi 0 to psi n, is just this matrix equation that you see right here. And so what I do is like, this is my Hamiltonian. This is like h psi is equal to e psi. And this is my new Hamiltonian. I've taken a continuous space into a discrete space, and now I've turned my Hamiltonian equation, or my Schrodinger equation, into a matrix equation. And so what happens is if I can find the eigenvalues of this matrix, which are the e's, then I solve my system numerically. So first I'm going to discretize using 10,000 points in x. They're going to span from -2 to 2, right? And remember, the well goes from -1 to 1. So I'm a little bit including points outside the well as well. And so my dx is just the difference in x, 0. So if I have 100,000 points between -3, actually I use -3 and 3 here, so I'll change that. -3 to 3. If I have 100,000 points, then my dx is 6 times 10 to the -5. It's a very small value. So what I'm going to do here is I have this matrix, and when I use the function I tridiagonal, which I imported at the top of the video here, there's a very specific way of using this function when you have a tridiagonal matrix. What you need to do is you need to define the main diagonal of your matrix. So that's this diagonal here. That's just, it's this here. So np.1's n gives me basically an array of n ones. And I multiply this by 2. And I divide, well, that's a 1. Multiply it by 2. And I divide by dx squared. So I get this here. And this corresponds to like 2 over delta x squared, 2 over delta x squared. And then I also have my potential. And my potential, it turns out, this is just a very fast way of making a well. This array here. So I have v naught, which is equal to -36. And if I want a well that's sort of, between -1 and 1, what I do is I create this array. So this array here is x is greater than or equal to -1, and x is less than or equal to 1, right? And so this gives me an array of like false, 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 and then when it's inside the well, it's equal to true. And I can convert this to floats, right? Gives me zeros, and then it's equal to 1 when it's inside the well. So if I plot this, plot this and I show it. I have to use plot.show now. Then I get basically zeros here, 1 when it's inside the well. I plot it as a function of x as well, so it's not a function of indices. And you can see that when it's in the well, it's equal to 1. When it's outside the well, it's equal to 0. And then I just multiply by negative 36. And I get the well in question. So this is just a quick way of making the well in this problem. And so I can delete all this. And so my main diagonal here is the 2 over delta x squared minus the potential. So this is my potential. It's minus v naught, x is greater than or equal to negative 1, and x is less than or equal to 1. And that basically gives me my v1, v2, v3, all the way to vn minus 1 here. So these are different on the main diagonal. The main diagonal, all the elements are going to be slightly different. And my off diagonal here, that's just equal to np.1s. There's going to be one less element, right? This gives me n minus 1 ones. So just 1, 1, 1, 1, 1, 1, 1. I take minus and I divide by delta x squared. That's just what you see here and the other off diagonal. So there's 2 off diagonals. They're both equal in this case. So then I have my main diagonal and my off diagonal, and I use this function. Now that I have this, it knows everything about the matrix, and I can solve for my eigenvalues, my energies, and my eigenvectors as well. And so I call these e's. This is method 2. It's the numerical method, and my eigenfunctions as well. I use this function here. I have to tell it what is the main diagonal of the tridiagonal matrix, what's the off diagonal of the matrix, and then this here, these 2 parameters here, I'm only looking for eigenvalues or energies that are bound. So it's between minus v naught and 0. It's the same assumption that we made up here, right? I said I'm only going to look for energies where minus v naught is less than e is less than 0. What this does is it saves this function here from solving for all the unbounded eigenvalues where the particle can escape from the well, and then you get crazy stuff with the wave functions. And so I get my energies and my size, and I can write my size like this, and I can plot the eigenfunctions. And by the way, the eigenfunctions of this method are a little weird. If I want the first eigenvalue of my size, I need to transpose this array and then take 0. And that gives me my first eigenfunction. And then I can plot sort of the probability density by taking the absolute value of the ground state, first state, second excited, and third excited state, just by squaring them. And these are what my eigenfunctions look like as a function of x over a. So the well is between negative 1 and 1 here. And you can see that there's a slight probability that you find them outside of the well, even though the energy is less than 0. So this is sort of the quantum region where in a classical problem, it couldn't escape the well. But for a quantum experiment, there's actually a probability that it's slightly outside the well. So that's kind of interesting. I also have my energies using method 2 as well. So e's method 2. And I get minus 34, minus 28.82, everything like that. I solved it in a completely different way. And I can compare these to these energies here. And they're actually very, very similar. And this basically last array here, it computes the errors between the 2 energies. So I take the absolute difference between them and I sort of divide. So it's a relative error here by taking the average between the 2 energies. And my errors are like 0.0006%, 0.0008%, 0.003%. And you see that the errors sort of increase by an order of magnitude as the energies get larger and larger. That's just something interesting to note by solving this. And so the percent difference between these energies are so small. So this makes us confident that the way that we're solving for these energies is a pretty good way of solving for them. Anyways, if you enjoyed this video, remember to like and subscribe, and I'll see you next time.